The more the merrier is a mantra of mine. There we go. All right, Chemistry 3111. Well, let's begin the summer semester. And for a lot of you, this is going to be a review, just a chapter where we deal with nothing but synthesis. If you took Organic Chemistry 1 at UCCS, this chapter, chapter 11, deals with chapters 7, 8, 9, and 10. So we'll say chapter 7 to 10, heavy on the 7, 8, 9, light on the 10. Why is it light on chapter 10? Because in chapter 10, there's only a few reactions that are covered in there. Halogenation, allylic bromination, anti-Markovnikov mechanism, and that's about it. All right, well, let's get into it here. And the first thing that you need to know for Organic Chemistry 2, for Chemistry 3111, are how to solve all the one-step synthesis problems that you would have learned in Organic Chemistry 1. That is a politically correct way of saying you need to know how to add any reagents to any synthesis problem that I give you where there's only one or two steps. For example, let's say we have this compound here. This is called isobutylene. And if I want to take isobutylene and I want to add 2 bromines to it, you can see here that we need to have Br2 in order to do that. So we'll put bromine. You could even be really fancy and say bromine is a liquid if you want to put in the phase of matter. And you know, some of my students have very inquiring minds and are always wondering about solvents. And for bromination, a great solvent is any kind of chlorinated solvent. It could be carbon tetrachloride. It could be chloroform. It could be dichloromethane. I'll just put dichloromethane in here. And again, it's not imperative that you add a solvent, but it's fun to do that. And there you go. That's the reagent that we need to do this reaction. If you want to take it one step further, you could practice drawing out the entire mechanism. You could say, well, I have a bromine bond like that. What's going to happen is I'm going to get the double bond acting as a nucleophile. Then I'm going to have a pair of electrons come in here. I lose the bromide, and then I'm going to form this intermediate. So let me draw intermediate, which is going to look something like this. Could anybody name this intermediate? It's got a funny name. Not funny, but it's just got a name that doesn't come up a ton. Could anybody name that ion? It's got a positive charge. This thing right here. Maybe yeah, maybe no. I don't know. Anyhow, yeah, absolutely. Yeah, thanks, Nick. It's the bromonium ion. Bromonium. Yeah, the bromonium ion. And when we form that bromonium ion, then we have bromide, which can behave as a nucleophile because you've got a great electrophile here. And the bromide can come in and it will attack and pop the ring open. And that gives you the vicinal dibromide as the product. And so there's just your first mechanism of the semester. And that's one that you would have learned already. Remember that when you have a bromine on one carbon and one on the next carbon, we call that vicinal. If they were on the same carbon, we call that geminal. So Gemini, like twins. And here you can see that David Klein himself says you have to master all of the reactions and the reagents required before you can take on any multi-step problem. How are you going to memorize all these reactions? For some students, it's flashcards. For other students, it might be, I don't know, maybe they come up with a limerick or something. For me personally, I've always found that just practicing, just practicing the reagents, writing them down over and over and over is the best way for me to remember those. But you've got to find some kind of strategy that enables you to memorize all the reagents to do all these transformations that I have on this slide here. This question 11.1 says, identify the reagents that you would use to accomplish all the transformations here. If you're having trouble, where would you find these reactions? They're all found in chapter 8, which is the alkenes chapter. So you can see that the starting material here is 1-methylcyclohexene. Thus, almost every reaction in here involves an alkene. Let's start with this reaction right here. if I want to add bromine, or HBr rather, across this double bond, the one that I have the yellow line on, would that be a Markovnikov or an anti-Markovnikov addition of HBr across that double bond? Not a trick question. I would never try to fool you.
Markovnikov?
Absolutely. It's a Markovnikov addition. How do we know that? Because if we look at the two carbons in the double bond, red pen here, this carbon is richer in hydrogens. And now it has two hydrogens attached to it. And so the rich are getting richer, and thus this is a Markovnikov addition. Could anybody throw me a reagent that you would do for the Markovnikov addition of HBr across the double bond? And again, it's not a trick.
HBr?
Heck yeah. Just use some HBr. Perfect. Okay, well, if we go counterclockwise, we go over to this one here, you can see that this is an anti-Markovnikov addition. Instead of the rich getting richer in hydrogens, now the rich is not getting a hydrogen, it's getting the bromine. So this is anti-Markovnikov addition. We do need HBr, but could anybody tell me, how do I change the reaction conditions so that I get the anti-Markovnikov product? Yeah, absolutely. Oh, I heard somebody unmute their mic, and I'm sure they had the right answer. Yes, you add a peroxide to it. Absolutely, absolutely. Perfect. Great, excellent. What do you want to try next? Let's just throw caution to the wind and go for this one here. This has nothing to do with alkenes. What about the one I have in the black circle? That comes from chapter 10, which is nothing more than a bromination. Can anybody tell me what the reagent would be for that?
ER2 with ultraviolet light.
Yeah, absolutely. So bromine, it doesn't necessarily have to be ultraviolet. It can just be, visible. But yes, absolutely, bromine and light. And this is a radical addition. So we'll put here, let's just call it radical bromination. And if you're listening to me and saying, where the heck would I find information about that? That would be chapter 10. Okay, that is found in chapter 10 only. Well, let's take a look at, this is a fun reaction. Taking that tertiary alkyl bromide, so one bromo, one methyl cyclohexane, and converting it into the alkene. You can see that we've got two types of beta protons, don't we? We've got the ones here on the methyl group, but then we also have the blue ones here, and it's the blue one that we need to rip off. And since the one on the methyl group, the one that I have in red, is less hindered, for that you would use a hindered base in order to pluck that off, like T-butoxide. However, if we want to make this Zaitsev alkene, we're going to use an unhindered or non-hindered base. Unhindered is the correct term. And thus we would use something like sodium ethoxide or sodium methoxide. Either one is perfectly fine. But what's next? Let's just keep going counterclockwise here. Let me ask you another question. This one here I have in the black oval. Markovnikov or anti-Markovnikov? What would it be? Is that a Markovnikov? Yeah, absolutely. Markovnikov addition of water. And therefore, I'm going to use just some regular old H3O plus. Now, if you're wondering, hey, Mr. Dion, I learned Markovnikov addition. I remember you saying that you could use mercury 2 acetate and water in the first step, and then sodium borohydride. So this is oxymercuration, demercuration. So you could use that in the second step. The issue, and there's no issue with the reaction. However, the only time that we use these conditions is when we can have a carbocation rearrangement. So use to avoid a carbocation rearrangement. That's when we use those conditions. Otherwise, we just steer clear of them. The next one is an anti-Markovnikov addition. It adds the hydroxyl and this hydrogen in syn fashion. And the way that we do that is using hydroboration oxidation. So the first step is BH3 and THF. And the second step is hydrogen peroxide and sodium hydroxide. That's a reaction that I covered the mechanism, or I go over it in Organic Chemistry 1. However, it's one of those things that I don't expect you to write out the mechanism. Just have an idea of the rationale. What's next? Here we go. How would you, let me get the highlighter up here. How would you describe this reaction? Can anybody give me the name of this reaction? The one I have in the yellow circle.
Hydrogenation.
Yeah, hydrogenation, absolutely. Hydrogenation. So if you've ever heard of partially hydrogenated vegetable oils and you're wondering what hydrogenation is, well, it's nothing more than adding hydrogen across the double bond of an unsaturated fat. And so that's what we're doing here. We're adding hydrogens across this double bond. And to do that, we just need some hydrogen gas, so H2. And there are several catalysts you can use, palladium, platinum, or nickel. You know what? Nickel doesn't get a lot of love, so I'll put the nickel in here. And we'll put here PT or PD. Either one works. Next one is the bromination reaction that we looked at. It was the first reaction that we covered, Organic Chemistry 2. Remember that that's an anti-addition of bromine across a double bond. And so for that, we would use bromine. And you can put a solvent in if you want. We could even put carbon tetrachloride in. The next one is, so this one here is a hydrohalogenation, hydrogen and halogen. This one here is called a halohydrin, okay? A halohydrin formation, because you have a halogen and a hydroxyl, which are added in the anti-fashion. Now, the only difference between this and the bromination is that you need bromine to form a bromonium ion. However, the nucleophile is not going to be the bromide in this case. The nucleophile here is going to be water. And so you run the reaction in water as a solvent. Bromine isn't highly soluble in water because bromine is nonpolar and water is polar. However, it's partially soluble because bromine is somewhat polarizable and can have an induced dipole in it. And another important factor of this reaction is that the hydroxyl is not only added anti to the bromine, but it's added at the most substituted carbon. Okay, we got 3 left. Next one is the formation of a transdiol, so that would be anti-addition of hydroxyls across a double bond. Anybody get any ideas about this? You can type it in the chat or unmute your mic.
Is it first with RCO3H and second with H3O plus?
Yeah, absolutely. Absolutely. So we'll put RC3OH. And then in the second step, we use just aqueous acid to blow that ring apart. Remember that there are several types of peroxy acids, or several peroxy acids that I would accept. For example, MCPBA. Another one that students sometimes use is peroxyacetic acid, which is this acid right here. They both serve the exact same function. Okay, next one is the formation of a syndiol, which is, or a cis-diol, I should say, which is formed by syn addition. And there's several conditions that we learn to do that. And I'll give you the time to, or I'll let you go back and investigate every possible method that we looked at. The one that my students seem to like the most over the years has been using a catalytic amount of osmium tetroxide. We'll put here catalytic amount. And then you use NMO, which stands for N-methylmorpholine N-oxide. So NMO is, let's see here, it's N-methylmorpholine N-oxide. It's a really interesting compound. That's NMO, which is a co-oxidant. Anyhow, I'm never going to ask you the structure of NMO, but these are the favorited conditions of my students over the years. And we have one reaction left. And you can see that what we're doing is we're somehow slicing this bond, and then we're adding oxygens on each end of the two new double bonds that are formed. So this is an ozonolysis reaction. The first step is to use ozone. So we just use O3. And the second step is to use dimethyl sulfide. And if you're wondering what the heck is dimethyl sulfide, DMS is just two methyl groups with a sulfur in the middle. It's like the sulfur analog of dimethyl ether. Very, very stinky compound. It's a gas. Temperature, oops, where am I here? And yeah, that pretty much covers all the reactions that we learned in chapter 8. Remember that our book goes over a few different ways to do this. You know, they teach you sodium thiosulfite and sodium bisulfite with osmium tetroxide. And what else? They teach you KMNO4 and hydroxide, and that works too. Those are all legitimate ways of doing that. And again, I'll let you go back in chapter 8 and take a look at that on your own spare time. But again, this seems to be the preferred method of doing the syn addition of alcohols across a double bond. Here we go. Good review of chapter 8. Well, let's move on. We're not moving very quickly through the first few slides, are we? Chapter 9. Okay, here we are. So you look at question 11.2. It says, identify the reagents that can be used to accomplish each of the following transformations. If you're having trouble, the reagents appear in chapter 9. So this is a great review of all the different things that we would have learned in chapter 9. Just to speed things up a little bit, I'm just going to cover these. I'm sure that most of my students remember most of these reactions. And why don't we start right here? We're taking propine or methylacetylene, either way, and we're adding one equivalent of HBr across the double bond. So we can write here HBr, and we only need one HBr. We'll put here one equivalent. And what I mean by equivalent is if I have 1 mole of this, I only need 1 mole of this to make 1 mole of this. Because if I add excess HBr, and so we'll put here HBr, and it wouldn't matter if you added 1 equivalent. This could be excess HBr. Then it's going to add a second equivalent of HBr in a Markovnikov fashion. And I told you that this is one of those mechanisms, especially this one here, that's not all that well understood. Now, if we want to take either a geminal dihalide or a vicinal dihalide, and we want to convert either of those to a triple bond, to a terminal alkyne, the way that we do that is by using a two-step process. The first step is to treat the dihalide with excess sodium amide. So excess, so we'll put here 1, is excess NaNH2, which does the double elimination. However, once that is done, you end up with an alkynide, and it needs to be protonated. In order to protonate that alkynide, we put in some water, which serves as an acid. It's not a strong acid, but it's strong enough to protonate an alkynide, which is a relatively strong base. You can see that here for the vicinal dihalide, we would use the exact same reaction conditions. Excess sodium amide, followed by treatment with water. Let's see here. Let's try one. I'll ask you guys. This one here, I want to make a methyl ketone. Now this methyl ketone is formed by the Markovnikov addition of water across that triple bond, which gives us an enol. So we end up with this compound here, but that enol undergoes tautomerization to give us the methyl ketone. Could anybody tell me the conditions that I would use to do that Markovnikov addition of water across a triple bond instead of a double bond?
You would use hydrogen sulfate or H2SO4 and then water and then mercury SO4.
That's right. You use sulfuric acid, put in some water, and then you need mercury 2 sulfate or mercuric sulfate in order to promote the reaction. What it does is it enhances the reactivity of the acid towards the triple bond. And it's something that I mentioned very rapidly in Organic Chemistry 1. And we actually talked about what's called a mercurinium ion, which is similar to an oxone, or similar to a protonated epoxide, or similar to a bromonium ion, similar but different, but it's the same rationale. It's not a mechanism I ask my students to know, but yeah, sort of the key ingredient here is the mercury 2 sulfate. Now the next one is an anti-Markovnikov addition of water across the triple bond, which gives you a different enol, where you have the hydroxyl over here, and then that undergoes tautomerization to give you an aldehyde. In this case, it's just like the anti-Markovnikov addition across a double bond. We need to employ boron. But now, instead of using borane THF, we use a hindered borane, which prevents the double addition, since you have two pi bonds in a triple bond. And so there's many different hindered boranes we can use. A favorite of my students is what's called 9-BBN, which is a borobicyclononane, followed by the same second step that we saw in the alkenes chapter for the last problem. So where it says 9-BBN, you can write R2BH. You can also put dicyanamyl boron, so dicyanamyl boron. That's one that's covered in our textbook. Sometimes in the ACS, you'll see them just write something big and bulky like this, just a shorthand for there being something big and bulky. Let's see here. Next one is one where we change the carbon skeleton. Kind of cool. We're taking a compound that has only 1, 2, 3 carbons, and we're converting it into something that has 1, 2, 3, 4 carbons. And so the way that we do that is by deprotonating the terminal alkyne. First step, we treat it with sodium amide, and that makes the alkanide, which is also a dandy nucleophile. And then for a nucleophile, we would use iodomethane. So iodomethane is going to add a methyl group, and the reactions on the far right are just a group of different ways of reducing the triple bond. If you want to reduce it to a cis alkene, like we have on the top, for that you would use hydrogen gas and Lindlar's catalyst. On the bottom, where you want to convert it to the trans alkene, you would use sodium metal reduction. So we'll put sodium in liquid ammonia, and that goes through what's called a radical anion, and that's why you get the trans isomer. And then if you want to completely reduce it, you would just use your standard hydrogenation conditions, hydrogen with palladium, platinum, or nickel. Moving on from there, the next one, if you just want to add Br2, so 2 atoms of bromine, for that I would write Br2, and I would put 1 equivalent. The next one, you want to just brominate the heck out of the thing, so you need to add an excess of bromine. So for that, instead of writing out the word excess, which just means more than enough, in organic chemistry, we just write it like this, excess. There used to be an Australian band called In Excess, and that's, anyhow, I'll just leave it at that. So excess, Br2, and the last reaction on this slide is where we're cutting up the molecule again. Here we have 1, 2, 3 carbons. But in acetic acid, we have 2 carbons, and over here we only have 1. So we're cutting the molecule here. The first step is to treat it with ozone. Please tell me it didn't erase all that. Good. The first step is to treat it with ozone. Where's my eraser? So yeah, step 1, O3. Could anybody tell me what the second step in ozonolysis of an alkyne is? Not DMS.
H2O.
Good. Perfect. Just in plain old H2O. All right. And there we have it. Somebody I knew was working at a fish plant in Nova Scotia, and they hired somebody to clean the fish plant, and anyhow, the person was hired to clean it, and so they cleaned it. And the owner came in and he said, "Wow, it smells so good in here. What did you use to clean it?" The person said, "H2O." And he said, "Good, buy some more." All right, well, let's move on to section 11.2, functional group transformations. How do we move functional groups around? You know, something that you want to review in this class is functional groups. We don't look at that many functional groups in organic chemistry. one, really. I mean, we do some, but things like esters and carboxylic acids don't come up a ton in that class. And so you want to make sure that you review your functional groups before Organic Chemistry 2 really kicks into high gear. But it says here it's logical to review two-step synthesis strategies because they can enable you to move a functional group from one carbon to the next. Let's say we want to move this bromine, this secondary bromine, and make it into a tertiary bromine. Well, how do we do that? Well, you're not actually making it into that. You have to do a series of steps to move the bromine around the molecule, as it were. First, we have the bromine, this carbon, and then how would we do an elimination? Because there's two types of beta protons. We have a beta proton here, and we also have a beta proton here, and both of those are unique. If you were to remove the proton that I have highlighted in red, you wouldn't get the Zaitsev product. You'd end up with this product, which is the Hoffman product. So I don't even want to make this product. I want to make the Zaitsev product. And so for that, I'm going to use the less hindered or a less hindered base or an unhindered base. And so I'd use something like sodium methoxide or sodium ethoxide. And then to do the addition, since this is a Markovnikov addition of HBr, just like we spoke about a few minutes ago, I would use HBr because it's going to give me a Markovnikov addition. If you haven't taken organic chemistry in a couple semesters and you've forgotten why is that, why do the rich in fact get richer? The reason why is because it proceeds through the most stable carbocation intermediate. Check this out. If you add the hydrogen to that carbon, what you end up with is a tertiary carbocation, which is stable. And then the bromide can come in and act as a nucleophile and attack that carbocation or give you the product. However, if it added in anti-Markovnikov fashion, I'll just draw it. So anti-Markovnikov fashion, then what you'd end up with would be this. So the question is, what's more stable, a tertiary carbocation or a secondary? Well, the answer is a tertiary is much more stable, and that is why Markovnikov addition proceeds the way it does. You can see those two reactions here. Sodium methoxide to make our Zaitsev alkene, Markovnikov addition with HBr to give you the tertiary alkyl halide. Also, if you wanted to do the anti-Markovnikov addition of HBr, we see those conditions here. Again, that is something that is covered in a lot of detail in chapter 10, including the mechanism. In the mechanism, really the reason why this happens is because you produce a bromine radical, which ends up adding to the less substituted carbon. Why does it do that? Because you end up making the more stable radical. If you look at the product from these three fishhook arrows, what you end up with is this, where I have the radical at the most substituted position, and then of course you do a hydrogen abstraction followed by a termination to give you the product. What else? We have the Hoffman alkene here, and I mentioned a hindered base, but T-butoxide would be a hindered base. Other examples would be things like DBU or DBN. You can even use hydride here, like sodium hydride, because it's a poor nucleophile. It's a poor nucleophile. It's a great base because it's so non-polarizable. What else? We have anti-Markovnikov. Let's keep moving from there. What if you have an alcohol, right? You can see that the first new chapter of material in this class deals with alcohols. So here we have an alcohol, and an alcohol in itself is a very crummy leaving group, right? There's no way that this can just leave by itself. That can't happen because hydroxide is the conjugate base of a weak acid. That means it's a poor leaving group, and so it has to be converted into a good leaving group. How do we convert it into a good leaving group? Well, we convert it into a tosylate by treating it with tosyl chloride and pyridine. And what it's going to look like then is we don't write OH, we write OTS. And this is a good leaving group. It's the conjugate base of toluene sulfonic acid, which is a very strong acid. What else? We can see the Markovnikov addition of water here. We can see anti-Markovnikov addition of water here. We see Markovnikov addition of water here to avoid a carbocation rearrangement. We see the formation of the Hoffman product here. And we see another anti-Markovnikov addition here. All right. So you see how we have to modify the approach when we go from a bromine to an alcohol. Why? Because a bromine is a good leaving group, is a bromide, because it's the conjugate base of HBr, which is a strong acid. But again, hydroxide is a strong base. It is not a good leaving group. It is the conjugate base of a weak acid. Let's see here. Some other fun reactions that we've already reviewed today. Markovnikov, elimination. We could kind of look at these, both this direction and this direction. So if I want to form the Zaitsev product, so I'll just write Zaitsev product over here. Well, that's going to result from me removing this proton in red. If I wanted to form the double bond at the other position, then I'm going to have to remove the proton in blue. So there we go, like that. And so you need to know when to use a hindered base or a non-hindered base. If you wanted to take this alkyl halide and make the more substituted alkene, you would use an unhindered base, whereas if you want to make this exocyclic alkene, which is less substituted, you would use a hindered base, like T-butoxide. And this is a little blip here that I stole from David Klein, and it might seem kind of harsh, but it says we have no chance to get this far unless we can easily recall all the possible reagents and reaction conditions first. That's just a nice way of saying you need to know all the different reactions that are learned in Organic Chemistry 1 in order for you to begin and really get into the new material in Organic Chemistry 2. Let's see here. There's nothing really new on here at all in terms of what we talked about today, but one reaction on here stands out and that we only covered it once today, and that is radical bromination. For your first quiz in Organic Chemistry 2, just like Organic Chemistry 1, in order for you to do anything with a hydrocarbon, it always has to start with a radical bromination. So bromine and light. It's the only possibility is that radical mechanism where you have the initiation to make the bromine radical, a halogen abstraction followed by, halogen abstraction followed by a hydrogen abstraction, followed by a termination to give you the tertiary alkyl bromide in this case. And so if you were to be given ethane, pretty boring molecule, but if you were given ethane, the only possibility you have is to treat that with bromine and light, which is going to brominate it to give you ethyl bromide, and then you could treat that with sodium ethoxide, which is going to do an elimination. So you could practice drawing your mechanisms here. So the ethoxide is going to rip off this proton, form the double bond, you lose the leaving group, and that's going to give you ethylene, as is shown here. Well, with all that information in mind, let's see if we can tackle some problems. Some synthesis problems. So it says here, propose a synthesis. Remember, the key word is efficient synthesis. Something that's really fun in Organic Chemistry 2 that really separates it from Organic Chemistry 1 is that instead of only having one way of making a compound, in this class, as the course progresses, you'll find that you'll learn 2, 3 different ways, maybe even 4 different ways to make the same compound. And so later on, we'll see that you'll have multiple answers that will be correct. However, for this one, I really only see one possible way to solve A. We know that we have an alkyne, and so the only way that we know how to make an alkyne is from either a geminal dihalide or a vicinal dihalide. And thus, the best thing for us to do would be to make a vicinal dihalide since we're given an alkene. We can make a vicinal dihalide from an alkene. What would that look like? It would mean that I would take my alkene and I would treat it with bromine. I'm going to leave the solvent out just for fun. And that's going to give me the vicinal dibromide, like this. And now I know that just through a couple of steps, I can convert that to the alkyne. Can anybody tell me what the steps would be to take that vicinal dibromide and convert it into this alkyne? I'll try to draw it to the best of my ability. Sorry, I'm having some problems with my laptop here. What would be the conditions I would use if I want to make that terminal alkyne? Yeah, thanks, Emily. Absolutely. The first step would be to treat it with excess sodium amide. And then in the second step, to treat it with water. There you go. I would implore you that before you get into quiz 11, make sure you review this mechanism. All right, make sure you know how to do that double E2 reaction followed by proton transfer. Let's take a look at B. So let's take a look at B. All right, so I have a primary alkyl halide. Where's my green highlighter? In B. And I want to first do an elimination, don't I? Because I want to put the bromine over here. And so I think the best way to do that is to do a retrosynthesis. If I had this exocyclic alkene, this is called methylene cyclohexane, what I have drawn in red. In order to take that and convert it to the final product, all I'd have to do is treat it with HBr and do a Markov-Nikov addition. And so now the question becomes, well, how do I get from here to here? How would I do that? The way that I would do that is by removing this proton in an E2 fashion. What would I want to use here, a hindered base or a non-hindered base, do you think, with the primary alkyl halide?
Hindered.
Yeah, I'd want to use a really hindered base, wouldn't I? Why? Because this is primary. If I use a non-hindered base, what I'm going to mostly get would be SN2. And I want to avoid as much SN2 as possible. And so I would use, I don't know, pick your base. My students like potassium T-butoxide, and I do too. So we'll put here potassium T-butoxide, which would give you the compound that I have highlighted in red. And if you wrote DBU, that's fine. There's nothing wrong with that, or DBN. And we'll put here in step 2, HBr. Okie doke. Let's see. Okie doke. Next one. I didn't give myself a lot of room here. Let's see if I do this. Okay. Next one. I'm taking this exocyclic alkene and I'm converting it to this more substituted alkene. There's not a lot I can do with this compound, really. I can either do a Markov-Nikov or an anti-Markov-Nikov addition to it. Anybody get an idea? Would you do a Markov-Nikov addition across this or anti-Mark? And it could be HBr or H2O. Either one, you'll be able to get the product. Yes, Sandrina, absolutely. Absolutely. Just give me 1 second, everybody.